I'll just start off with a quick overview. So first, a short introduction, what this is all about. Then I'll talk a little bit about the ARM architecture, just to give some very basic overview for those who are not familiar with ARM yet. And then the main part of this presentation will be the case study, where we'll be looking at ARM assembly code produced by GCC and Clang to see if there's any code generation opportunities we can use on the LVM side. And then I'll just conclude with a short summary. So what is the motivation for this talk? The ARM LLVM backend has been around for many years already. It's very mature. It produces really well-performing code. However, LLVM is also increasingly used in the embedded space, where code size is much more of a concern, or even the primary concern. So the goal of this talk is to take a real-world application where code size matters, and then just compile it with Clang and GCC, and then have a detailed look to see where we can improve on the LLVM side. But first, a couple words about ARM. So the ARM architecture is a classic RISC architecture. Started out as a 32-bit architecture, then later on was extended to 64-bit as well. It's a load store architecture, and three important characteristics are the barrel shifter, so that essentially for many arithmetic operations, you get to do a free logical operation as well. So in the example here, we have an addition, and we also get to do a logical shift left on one of the two source operands. There's also powerful indexed addressing modes. So those are useful. So essentially, they give you, for the memory operations, they give you a way to update the base pointer. So this is very useful when you are, let's say, iterating through an array. Then you can essentially get the update of the base pointer for free as well. And then there's also predication. So every ARM instruction has a 4-bit condition code. And this is a very convenient way of executing the instructions conditionally without having all the overhead of having additional branch instructions. And there's also not just one ARM instruction set. So over time, the architecture has evolved into a family of instruction sets. So there's the original 32-bit ARM instruction set. And then later on, thumb was introduced, which is a subset of the original ARM instruction set, but with a much more compact encoding. Thumb instructions are only 2 bytes long. And then eventually, thumb 2 came along, which tries to give you the best of both worlds, which is performance similar to what you get with the original ARM instruction set, but code density closer to what you get with thumb. And today, if you compile for 32-bit ARM, typically what you choose is thumb 2. And this is also the focus of the talk. So all of the assembly code shown in this talk, all of that is thumb 2. And the base ARM instruction set only covers integer operations. So if you want to have support for native floating point operations, the CPU can implement one of the instruction set extensions. So there's VFP and also the Neon instructions for SIMD. And as mentioned, the goal of thumb 2 is to really give you the best of both worlds. And in order to achieve this, the instructions are variable length. So there are instructions which are 16-bit long, but there are also instructions which are 32-bit long. And from the instruction set, you have access to all of the 16 general purpose registers. And depending on whether the CPU implements one of the instruction set extensions, there is a floating point register file as well. In order to conserve instruction space, instructions no longer have a 4-bit condition code, but there's a new instruction called IT, or if-then instruction, which allows you to execute up to four instructions conditionally, and they can be predicated on with the predicates passed to the if-then instructions or the inverse of that. So here's a really small example implementing an if statement with predication with the it instruction. So you can see we are doing a comparison here. Then we have our if-then instruction, and if the condition matches, then we execute this instruction, and if not, this instruction gets executed, and then we have either R2 or R3 in our destination register R0. So yeah, so much for just a quick ARM introduction. For the case study, we've chosen an application developed by Samsung, which is very much optimized for microcontrollers. And so code size is something we care a lot about for this. And the application is JerryScript. So JerryScript is a really lightweight JavaScript engine. So it's heavily optimized to run on microcontrollers. So it has a base footprint of 10 kilobytes of RAM. So you can even get this running on a device, let's say 32-bit kilobytes of RAM microcontroller that works just fine. And so usually the first question that comes up when we talk about JerryScript is, why do you even want to run JavaScript on a microcontroller? So the answer to that is that the idea here really is there's just so many JavaScript developers out there, and a lot of them would be interested to develop for low-end systems, but a lot of them also don't want to learn C. So with JerryScript, we want to give them the ability to develop for embedded systems with the tools they're used to. And yeah, that's kind of the motivation behind this. JerryScript itself is written in C99 for maximum portability, and it supports all of ECMAScript 5.1. So this is not just supporting some subset of JavaScript, it's really the full thing. And it passes the Test 262 conformance test suite. So yeah, all the features are there. And the project is open source. And one motivation for this talk was also that the JerryScript developers themselves, they want to use Clang for, today they can use Clang already for debug builds, but the idea is also to use Clang for release builds. But code side-wise, we are not there yet. So yeah, that's hopefully in the future, the code size will be good enough to also compile JavaScript with Clang. And just to give you an idea of what kind of target hardware this is all about. So this is a STM32F4 developer board hosting a Cortex M4F. And the board has 192 kilobytes of RAM and 1 megabyte of flash. So you can see there's not too many resources there. And this is probably even one of the beefier embedded microcontroller boards. So before I show some measurement results, I just want to say a couple of words about the different compiler versions being used. So there's, on the Clang side, we have a trunk snapshot about 2 weeks old now. And on the GCC side, this is a 5.2 Linaro bare metal toolchain. And JerryScript is also a trunk snapshot, which is about 2 weeks old. And we only focus on the release build here. And the build itself is optimized for the Cortex M4. And obviously, we're building with Dash OS. And the build is a static build. So there's no, so the binary runs bare metal. There's no operating system involved, and also no libc. JerryScript has its own very small and limited C library implementation. And yeah, so here's a chart showing the current code size numbers. So the blue bar is what we get with Clang. So that's 231 kilobytes. With GCC, we are at 208. So we are about, the Clang-generated binary is about 10% bigger. And then with GCC, we can also enable LTO, which brings us down below the 200 mark, down to 190. So that also helps quite a bit. And if you're wondering why there's no Clang LTO number, here's why. So right now, if you want to do an LTO build and you pass the Dash OS option, then it will just error out and will complain that the Dash O option requires a number. So there's basically no optimization pipeline set up for code size. So that's still something that's missing. But I would assume that once this is added, we should also see a good code size improvement with Clang LTO, just by the fact that there's more context to optimize, more dead code which can be detected, things like that. So even without doing any specific code side optimizations, I would think that there's already some improvement there. So yeah, okay, so now we know that our Clang-generated binary is bigger. How do we find interesting functions to look at, or how can we improve this? So the good thing with code size is that you can do everything static. You don't even need to execute your binary. So we wrote a Python script which just parses the object dump output and then computes the size of the different functions. And if we do this both for the Clang-generated binary and the GCC-generated binary, then we can compute a code size delta for the individual functions. And then we can look at the functions which have the highest absolute difference or the highest relative difference. And that way we can really see functions which are interesting or where things are going wrong, where there's room for improvement. And this is the binaries used for that, they were also compiled with inlining turned off. But this obviously changes the binary, but there's only very limited inlining done anyway if you compile at Dash OS. So overall, that doesn't make much of a difference. And then there are also some functions get specialized by GCC, so sometimes you don't have the same function in both binaries. Yeah, the overall results, they are not perfectly accurate, but it's definitely good enough to see, to find interesting functions to look at and do a closer investigation. So in the following slides, I'll just want to show a couple of examples. And I've mostly focused on really small functions in order to still make them fit on a slide. But there are also several large functions which have big differences. But from what I've seen, the code generation deficiencies in the large functions, they are kind of same instances of what you see in the small ones. So I don't think we get a totally different picture by just looking at the smaller functions. And yeah, so this is a very small function so JerryScript has a C API to interface with C code, and one core data type is the Jerry API value type, and this is effectively a struct. which has two fields. One of them is a type of the value, and then there's also a union which carries the actual contents of the value. And here we have a function which just creates a null value. So for the null value, we allocate a new object on the stack here, and then the type field is written, and then the entire struct is returned by value to the caller. And looking at the GCC-generated code, we can see this is actually quite compact. So it's just 6 bytes. And we have this move instruction here. So the 2, that's actually coming from this constant here. So this is this type is an enum, and GCC turns that into or uses an 8-bit value for that enum, and just writes it and then returns. On the clang side, however, things look a little bit different. So we can also recognize the move here and then the write, but then we can already see one difference here. So this is actually a 32-bit store. So that's same. So clearly GCC is a bit smarter about using the smallest possible data type, and that helps to, if they're constant lying around in the data section, that already helps to reduce the size of the binary. And then also we see that there's some space allocated on the stack here, and then later on that the contents of the stack are loaded into registers and then again stored to the R0 contains the address of the space for the return value. So essentially what happens here is that the uninitialized data of this struct is copied around. So that's obviously redundant work being done here and could be eliminated. Then we have another function here. So this is also very simple. It has 3 arguments. Those arguments are used to initialize a bunch of global variables. So all of those are global variables. And then we see a fairly consistent pattern in Clang here, where the base address of the global is being materialized with 2 move instructions. And then there's a store for every argument, writing to memory. And looking at the GCC, so one thing we see here already is that the addresses, they are actually adjacent to each other. So all those 3 globals are next to each other in memory. And GCC detects this and takes advantage of this by just emitting a single store multiple instruction. And it also does not materialize the constant, it rather loads it from a constant island here. And generally, if you compare the code size required for materialization of an arbitrary 32-bit value, you can see that we save 2 bytes if we go for the constant island. So if we just look at it from the code size perspective, that gives us a 2-byte improvement. And depending on how many constants you have, this can add up quite a bit. So this is just a small wrapper function around the mem decompress pointer function. And essentially all it does is checking for null here. And we can see this in the GCC-generated code. There's a compare and branch if 0 here, which is implementing the check above here. So that's very compact. And then we have, so we can see here that this is a tail call, so nothing happens after this call anymore. And GCC takes advantage of that and really optimizes it. It doesn't allocate any stack frame for this function. And Clang still emits also the compare and branch if 0, so that's great. But then it allocates a stack frame here for calling the function. So I know that we have some tail call optimizations also in the, I think also in the ARM backend. But looks like this case is not triggering that. So this is a slightly bigger function. Essentially, all it does is convert an integer to a string. and it's a fixed width integer, so it just goes backwards, builds the string from the back to the front, and doing some computation here, so essentially a modulo computation, and then just adding up the ASCII value of the 0 character. So looking at the generated code, we see that the entry basic block looks very similar, so there's almost no difference, except that clang also materializes another constant here, which is later on used in the actual computation. And when looking at the GCC-generated code, we can see that the code for the modulo computation is actually quite compact. So there's just a signed division here, a multiply, subtract, and then the ASCII value of the 0 digit is being added, and then it's written to the string buffer. On the clang side, however, there's quite a lot more being generated here, so it's also doing a multiplication and then a lot of additions, subtractions, and here it's really using the wide form, so this increases the code size quite a bit. And yeah, then there's also a bit more overhead here for the loop management. Another example here, so if you take a closer look, you can see that here the macro invocation is the same. It's only those functions are identical except for the assert, but since we are doing a release build, the assert is removed anyway. So what we end up with is identical code for both of the functions, and clang is GCC is a bit smarter here, so it actually detects this redundancy, and then the ECMA get string from value is just forwarded to the ECMA get object from value. And I know that we also in clang have same code merging pass, but it seems it doesn't detect this particular case. Another function here, which is essentially, so this is the literal storage, and there's just another type check here, and then we have another tail call. And similar to the other example, we can see that GCC detects the tail call, optimizes it, no stack frame being allocated, and also the checking this condition above is a little bit more efficient here than what clang emits. So clang even emits some conditional code here, and yeah, overall this is much more compact. This is from the libc fatal. So what it does, it gets a bunch of arguments. Those arguments are checked to be non-null before they are passed to printf, and then there's just an abort being invoked. And the GCC-generated code looks quite nice here. So there's essentially a compare and branch if 0 for all the individual arguments. And yeah, once those have passed, then there's just some setup of the arguments, and then the printf is invoked. On the clang side, the code is less compact here, so we have also one compare and branch of 0, but then to check the other two arguments, there's actually an additional compare, which is much bigger than the compare and branch if 0, and then there's even another predicated compare here. So yeah, this is a bit bigger. Then we have another case here. So this is just a very simple function checking whether a character is a valid hex digit. And so that's actually one of the few cases where I saw GCC also emitting an if-then instruction. And yeah, so the clang-generated code again even predicates 3 instructions here, and yeah, the whole thing is quite a bit more code. Okay, so that already completes all the examples I wanted to show. Let's just have a quick recap of what kind of code generation issues or potential for improvement we can see here. So obviously one consistent pattern is that GCC is using constant islands rather than materializing a lot of constants. GCC is more effective at using the compare and branch if zero. So I saw a couple more cases where Clang was doing a bad job there. And also the same code merging, that's, I know we have in Clang some basic infrastructure for that, but yeah, needs further investigation to see why it didn't catch this instance. Then switch lowering is quite different. So I didn't show any example of that. The code generated for switches is quite different. But for most of the cases I saw, even though it was done quite different, there was not really a big difference in terms of code size. And yeah, tailcal is definitely something where GCC is catching. I think I didn't really see any case where it didn't catch it, but yeah, maybe they were not complicated enough. As we saw in the very first dump, the GCC also is doing a much better job at using small data types, just using the smallest data type as possible for the enums. And also the computations seem to be a little bit more compact. And LLVM tends to emit a lot of if-then instructions. So I guess there can be some tuning there. Okay, yeah, that brings me already to the summary. So overall, the Clang-generated binary is about 10% bigger. I think that's not too bad, to be honest. I expected it to be, the difference to be higher. So I think that's still not too bad. And as you've seen, a lot of the stuff is, I would still consider low-hanging fruit. It's not extremely difficult to fix. And I think one work item for the future is definitely to get LTO working. And then also, yeah, improve the same code merging pass, and also, yeah, I mean, you can even do things like reverse inlining, or I think there's a lot of low-hanging fruit to fix first. Yep, that's it. Thank you very much. So any questions?
Did you actually try to compare with some other compilers?
Say it again?
Did you make any comparison with other compilers?
No.
Just two versions of tools, and well, and for one application. So did you try to do more systematic?
No, I just so this was really just looking at Clang versus GCC, and just on this particular application. So I didn't look at any spec benchmarks or things like that. Yeah. Yes.
Yeah, thanks very much for the talk. It's very good.
Sure.
Obviously, there's a bit of work to be done yet.
Yeah.
So I did about 2 years' work of this on the SNC compiler for Vita.
Okay.
And we actually used Thumb2 for O2 because the Thumb2 code generally is faster than the ARM code in the case where most of the code is cold because of the size of the iCache. So we're really optimizing for iCache performance more than we were for space.
Yeah.
Sort of some of the things we kind of, well, some of the things obviously some of the things on your list.
Okay.
The if then else is the branch prediction on the ARM CPU seemed to be really good. So particularly the CPZ instructions were very useful, and so the if then else's are not particularly useful, as you say. Yeah. Choosing lower range registers really important for generating the shorter versions of the instructions. And we had to make a lot of improvements to the register allocation to make that more likely. Although we still use occasionally use some of the R8 to R13 numbers as well. So there's there's a few things to do anyway. But,
yeah, definitely. Yeah. Yeah.
Anyway, good luck.
Yeah, thanks.
Thank you.
Any more questions?
Any questions?
So, do you have any plan to upstream this fixes?
Yeah. I mean, so I only started this a couple of weeks ago, so it's still kind of in the investigation phase, I would say. So I haven't really started to implement any optimizations, but I certainly plan over the coming months to spend some time on that, and I also upstream that. So
Yeah, and then you're filing some bugs to the Bugzilla. So
I haven't, but certainly I guess there's plenty of things I could file. Yeah. So would you have any specific interest in bug reports there, or?
So probably some people
Yeah.
will pick up some of the work. I mean, to get it fast and fixed.
Yeah. Yeah. I'll look into that. Yeah.
So I was wondering about the one thing you mentioned with this enum value encoding, whether it's a byte or a word. So that
Yes.
seems to me that would be a change in ABI. It's not just an optimization. So
But the ABI should be the same. So I compiled for
well, if the other side expects to read a word and the one side writes just a byte, it doesn't work.
Yeah. It might be a case that this is actually something which is not, which is just within one compilation unit. So it might not even go outside. I would need to check.
Just
Yeah.
something
Yeah.
that made me wonder. Okay.
Yeah.
Anyone else? If not, then let's thank Tilmann again.